Hi, welcome to the first module of lecture 15. In this lecture, we're going to take the stuff we did in the previous two lectures rather, on the basics, the fundamentals of multivariable calculus, and apply them to the core application that we learned them from in the first place, which is multidimensional optimization. Now, if you recall, optimization was the incentive for learning calculus in the first place. We said that the primary use of calculus in the social sciences, political science, was to optimize. Sometimes you're going to optimize, say, you're going to minimize your squared error, or you're going to minimize your loss function, or you're going to maximize your likelihood function, or you're going to maximize your utility function. And in all these cases, maximization and minimization is the fundamental goal that you're trying to achieve, and calculus helps you reach that goal. So that was the motivation behind the stuff we did in part 2 of the course, learning about calculus. That's also the primary motivation behind the stuff we're doing now in part 5 of the class, a multivariable calculus. There is in fact no difference. We are still trying to maximize or minimize things. And in fact, whereas before we had to come up with somewhat artificial examples, particularly in statistics, that had only one variable in them, right? In the real world, as we discussed a couple lectures ago, most things have lots of variables, right? There are lots of causes to most effects, lots of independent variables to describe a dependent variable, and so on. And so oftentimes we need to maximize and minimize functions of more than one variable. All that stuff we discussed in the previous couple lectures. Here we're actually going to provide the methodology to do that, using the stuff we did in the previous couple of lectures. The good news is, for most of this, all the intuition and frankly all the methodology we've done already. There's not much new in these cases. So if you think way back to part 2, the end of part 2 of the class had a lecture on optimization in one dimension, and we discussed the general rules for this. We took the first derivative, we found critical points, we checked the second derivative at each critical point to see if it was a local minimum or maximum, or neither. And we figured out from those facts if it was a local minimum or maximum, what I said, and then we compared those values at the point, the values of the function at those points, and said, okay, do we have a global maximum or global minimum? Fundamentally, that's all we're going to do here again, and I'm going to go through that much more slowly in a couple of seconds. We discussed the methodology for doing that, but the important point is the intuition behind that particular kind of optimization is exactly the same. There's no difference, nothing new conceptually, everything's exactly the same. The only difference will be in the complexity of the calculations, which we'll talk about very soon, and give some examples for as well. Now, before doing that, though, there is one sort of twist that comes up. What I just described was a method for computing an unconstrained optimization. What does that mean? Well, an unconstrained optimization is one in which there are no constraints on the values of the function of the parameters or anything like that, right? What does that mean? Well, a typical constraint, probably the most common one you experience in everyday life, well, there's a lot of constraints you experience in everyday life. For instance, you're constrained to walk along surfaces and not just float in the air, right? That's a constraint that affects where you can actually locate. That's physics, though. That's, being constrained to a surface is a general problem in physics, and these techniques work there as well, but that's the kind of problem we're going to be dealing with. The problem we're going to be dealing with here, the most common version of this, is a budget constraint, right? So you may want to spend all your money and buy 1,000 fancy cars and houses or whatever, but you don't have that much money, so you're constrained to spend within your means, more or less, ignoring debt for the moment. And this constraint is a budget constraint. What it does is constrain the number of things you could buy. Why is that interesting? Let's really quick just go through this. Let's say you have some utility for two things, right? Let's say apples and oranges. And let's have a really simple utility function, a plus o. So the more apples you get, the happier you are. The more oranges you get, the happier you are. How many should you buy of each? Well, in theory, an infinite number, right? If you're insatiable for apples and oranges, which is probably not the case in real life, but let's say you were, you would buy more and more forever. So if you had an unconstrained problem, there would be no solution to this problem. Your maximum of your utility would happen at an infinite number of apples and an infinite number of oranges. There's no maximum to that problem. Why is this relevant in political science? Well, let's say You have some function, you're a candidate, and you're ready for office, you have some function, and one of these things you have a function of is campaign spending, C. And let's say your function is increasing in campaign spending. So we can say that it's some function, let's say, of blah, 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 plus some alpha times C. So the more C you have, the better off, the happier you are, because the campaign spending buys you airtime and so on and so forth, right? Advertisements and such, door-to-door canvassing. And it helps increase your chance of winning. So you want more campaign spending. And if you had to maximize this function in an unconstrained fashion, right, you would choose an infinite amount of campaign spending, right? But as with apples and oranges, you have limited funds. So typically the kind of problem we deal with in political science is a constrained optimization problem. So the difference is unconstrained and constrained. And a constrained problem, you have constraints on what values the parameters can take. So for instance, the campaign spending might have to be in some set from 0. You can't spend negative money, you can't steal money from people. And some maximum, which might be your budget constraint, B. Same thing over here. Here you might think, now let's say apples cost $1 and oranges cost $2. Well, you would have 1 times A plus 2 times O. That's an O, not a 0. And that would have to be less than or equal to some budget constraint, right? Where the budget constraint may be B, say $10 instead. And also you have constraints that say apples must be non-negative and oranges must be non-negative, right? I'll put a little slash there, 0. Why? Well, again, you can't have negative apples or negative oranges. That makes no sense. So you're constrained to have positive values of these things, and you're also constrained not to exceed your budget. So in this case, because you have equal value for apples and oranges, but oranges are twice as expensive as apples, you maximize your utility by buying 10 apples. That satisfies, and 0 oranges, that satisfies this and this. You spend all your budget, as you'll see you often do when you have a non-satiable preference, and you get the maximum utility you can get out of this, which is 10. Had you bought 5 oranges instead, that would also max out your budget, but your utility would only be 5. That's how this stuff works. Those are constrained problems. Now, you've actually seen constrained problems a little bit back in part 2 of the class, although we didn't call them that. Whenever there were some bounds on the values of x, where you maximize their function, those bounds were constraints on x. Now, we didn't use any fancy techniques there. We just plugged in the different bounds and saw which were the bigger values of the function and the smaller values of the function, because that was easier. Here, we can't really do that. It's difficult to plug in values at the bounds when you have, say, bounds in 2 dimensions. There might be, a ring or an oval or some funkier line, and you can't plug in all the values of that circle or oval or a line or whatever into your function conveniently. So instead of just plugging things in, we're gonna use a more concrete mechanism to deal with explicit constraints on the values of the parameters. But conceptually, you've seen this before. If you constrain the values of the parameters to within some bounds, that forces you not to consider certain potential local minimum maximum that are outside the bounds. Recall that if you had a function that's like this, right? If you had unconstrained, right, this goes down forever, goes up forever, there are no minimum maximum that are non-infinite. But if my bounds are here and here, right, I change the nature of the maximization and minimization problem. In this case, the maximum might be here and the minimum might be here. If I move this bound on the right to the red spot, now the maximum is over here, but the minimum is still over here. And so on. If I move this one on the left over here, the minimum drops down to here. And so on. The point is, the bounds change the maximization and minimization problem. They change the optimization problem. Before we dealt with this just by computing the value of the function at the bounds as well and comparing, now we're actually going to come up with a concrete, more rigorous technique for doing that. That was not rigorous. That was not rigorous. But this is a little more general than before. And that's it. So the way the rest of this lecture is going to go is for each one, we're going to deal with three separate kinds of maximization of optimization problem. The first is unconstrained. We're going to start that in this module, and the next module we're going to give examples for that. I'll give an example of how that works. An unconstrained problem has no constraints at all on the values of the variables, meaning you can't have bounds on the parameters. It just has, you can choose from any possible value of the parameters in maximizing or minimizing. It's an unconstrained problem. That is what we're going to do in the next couple of modules. In the third and fourth module, we're going to deal with a very particular kind of constraint, which is called, in blue down here, an equality constraint. An equality constraint is when you're constrained to have some function of your parameters exactly equal to some constant. If you are forced to spend your entire budget constraint all the time, that would be an equality constraint. You must spend all your money, therefore you arrange your variables in such a way so as to spend all the money every time. You can't come in under budget. For instance, you're forced to spend the entire budget. That's an equality constraint. Equality constraints are more straightforward than the type I'm going to mention in a second, inequality constraints. Unfortunately, they don't often come up in social sciences because oftentimes we have more leeway in our actions, right? In physics, for instance, you're constrained to walk along the surface due to gravity, right? That's an equality constraint. You can't leave the surface by yourself without, being in a plane or jumping, for a short time, but in general, you're stuck to a surface. That's an equality constraint. You're constrained to be along the surface. However, you're not usually constrained to spend your entire budget. You're not usually constrained to always be zero in these A's and in these apples and oranges. You can be greater than 0 or equal to 0. Those are inequality constraints, which is the second kind of constraint, inequality constraints. Inequality constraints we'll find are trickier. They require you to deal with different cases, and we'll give an example of how to do that, give a method for doing that, and examples of how to do that in modules 5 and 6 of this lecture. Sometimes you can convert an inequality constraint to an equality constraint. For instance, if your preferences for something are insatiable or non-satiable, so you just want more and more and more of apples and oranges, then you will always spend all your budget, because since getting more of something gets you more utility, you will try to get as much as possible, which means always spending all of your budget. In that case, your budget constraint becomes an equality constraint because you always spend it all. You always have a budget, you always spend over here exactly equal to your budget over here. In general, though, we can't often do that conversion, and we'll have to deal with inequality constraints. So sort of to conclude this intro, this whole lecture is designed to teach you is designed to provide a methodology for doing different kinds of optimization problems, unconstrained, ones of equality constraints, and ones of inequality constraints. We are not, however, going to spend a lot of time talking about intuition or anything like that. And the reason is we've already seen all that stuff before, right? For unconstrained optimization, it's the exact same logic as we saw in one dimension. There's no difference. For constrained optimization, it's a little bit on the scope of this course to detail the whole geometric argument for how dealing with constraints leads to the methodology we use. So we're not going to talk about it much. We're going to focus on the actual process of calculating a constrained optimization problem. But the conceptual notion is pretty similar to dealing with bounds. The point is you're forcing the problem to lie within a certain region, and therefore forcing the problem, changing the nature of the optimization problem. That's it. Okay, so that intro. The rest of this module is going to be taken up just briefly discussing what the method is for dealing with an unconstrained optimization problem. And that's going to take a few seconds because it's the exact same method as before. So here are the steps for doing that. Step 1, compute the gradient of your function. That's step 1. This is the exact same analog to computing the first derivative of your function, except now you're computing the partial derivative for every component of x. You will have, if x, we're just going to say x is m-dimensional. Write a room there, m is supposed to be dimensional. So there's m dimensions in x, so there's x1 through xm. There will be m components to your gradient. That's step 1. Remember, these are all partial derivatives. So you have partial derivative of f with respect to x1, x2, and so on. Remember from the previous couple of modules, lectures. Step 2, just like before, we set the first derivative equal to 0. We are now going to set the gradient equal to 0 at the critical points x star. The only difference now is instead of having a single x star, it's a vector x star. And we're going to set that equal to 0. Now this is a little trickier, and this is 0 vector. In practice, this would be trickier because now we have actually m equations, right? So for every component, you have one equation. So you have df dx1 equals 0, evaluated at x star, vector, and then df dx2, evaluated at x star, vector, equals 0, and so on down to df dx m at x star equals 0. Now, if you miraculously ever have a completely linear function in which you have just, x1 plus 3x2 plus 4x3, or if it's not linear but it's completely separate, so all the so there's no x1s multiplying x2s multiplying x3s, then this is pretty easy. But in general, you're going to have a system of equations. There'll be m equations and m unknowns. You have to solve them simultaneously. This is the exact kind of problem that we did a whole bunch in the previous part of the course in linear algebra, in the middle lecture, where we discussed how to solve systems of linear equations. When these are linear equations, it's the exact same methodology. So you can use all the same methods we did there: substitution, elimination. You can use Cramer's rule. You can use matrix inversion. All the same stuff that we did before. Apply now if these are linear. If there's a system of linear equations. More generally, this would not be a system of linear equations. You have a system of nonlinear equations that may be extraordinarily hard to solve. You can try substitution, but it might not work. In general, if you have a really big system of equations that's nonlinear, you would not be doing this by hand. You would use some kind of computational aid. The textbook has a bunch of examples for them. You can Google online, algebra program. There are lots of them. A bunch of them are free. So that's in general what you're going to be doing there. We're going to give some examples to see how this works that are 2 or 3 dimensional. The book has 2 or 3 dimensional ones. We'll probably stick to 2 dimensional ones in the next module. Okay. So it's harder to write 3 dimensions on that tiny screen. But the technique's the same, and the book has examples of 3 dimensionals. Okay. That's step 2. Okay. Step 3. Compute the Hessian matrix. Now, recall from the previous lecture, the Hessian matrix was the matrix of second derivatives. Right? So if you draw that over here, I'm going to run a room rapidly. So here was, I'll do it for 2 dimensions, dx1 of f, and over here is dx2 x2. Recalling this means take the derivative, the partial derivative with respect to x2 twice. And over here are the cross partials, x1, x2, and x1, x2. Remember, this shorthand just means, for instance, the upper left shorthand means d squared f dx1 squared. Okay. This is a 2-dimensional Hessian. For 3 dimensions, it's 3 by 3. For 4, it's 4 by 4, and progressively bigger and bigger and bigger. Again, you're not going to be doing these things by and large by hand. For anything large, 3 by 3 is probably as large as you want to go by hand in doing problems. Okay. So there's a Hessian. That's step 3. This is exactly analogous to computing the second derivatives. Now what we want here is a Hessian evaluated at each critical point x star. Right? This is the exact same thing as computing the second derivatives in the method we use for 1 dimensions. and it has the exact same point. We can try to determine if this is positive or negative or neither, or 0 in that case, and here it's more complex. Okay. But the step is to compute the Hessian in general, and then calculate it at each x star, each critical value. Okay. Step 4. Step 4, start over a new screen here. Step 4 is to determine whether or not the Hessian is positive definite or negative definite. Now these things are exactly analogous to the cases of a positive second derivative in one dimension and a negative second derivative in the other dimension. So recall in one dimension, you had, if the second derivative were positive, you had a local minimum. If the second derivative were negative, you had a local maximum. Now the second derivative were 0, you had some indeterminate issues. So you had problems. So we're going to do the same thing here. Now, what's the analog to a second derivative that's positive? Well, it's the Hessian is positive definite. Recall positive definiteness was defined earlier in the previous part of the class. So again, you need to know all the stuff from before, have a good grasp of that stuff before you can go into this stuff. But a positive definite Hessian matrix indicates that, as we discussed in the previous lecture, positive definite Hessian matrix indicates that you have a sort of locally convex, so it's curved upward in all dimensions, right? So you can kind of visualize in 3 dimensions. It's like a bowl, right? It looks kind of like a bowl in 3 dimensions. I could try to draw a bowl, but I'd probably do poorly. But you can imagine a bowl, right? A bowl, inward, and it's curved upward in all dimensions. It goes up forever in theory, but the very bottom of the bowl is a local minimum. If it's globally convex, it's a global minimum too. Okay. So if H is positive definite, if the Hessian is positive definite, you have a local minimum. If H is is negative definite, then you have a local maximum, right? So negative definite is like a ball turned upside down, right? So it's going down in all directions, and it comes up to a single point. If it's globally, that would be a globally concave function. If it curves up in all cases, so an upside down bowl is like a globally concave function, and then the Hessian for that function is negative definite. In that case, the point up here, the critical point, is a local maximum. Again, just analogous to the second derivative being negative. Now, one issue comes up in that, and we'll discuss how to figure out if these things are positive or negative definite in a second. But there are 2 other cases to deal with first. One is what happens if you have neither positive nor definite? Well, there's really 2 possibilities we can consider. One, if the determinant equals 0, then we have an indeterminate situation. It's kind of like we had before when the second derivative was 0. The issue here, though, is that with the determinant equal to 0, we're just not going to learn anything else right now. And the reason is going higher order. What we did before was we went higher order. We took higher order derivatives and figured out if it was a minimum, maximum, or a saddle point. Here, though, if the determinant is 0, it's just indeterminate, and to figure out higher order derivatives would require computing 3rd and 4th derivatives potentially. A 3rd derivative takes you into the 3rd dimensional matrix, which is a tensor. 4th and so on. It gets really messy, and in general, it's just not going to come up very often enough to deal with this, so we're just not going to do that. So we're going to leave it by saying if the determinant's 0, it's an indeterminate case. The other possibility is it's not 0, but it's neither positive nor negative definite. In that case, you have a saddle point. And a saddle point, really, we discussed this earlier in 1 dimension, but a saddle point in 2 dimensions, 2 or more dimensions, looks a lot like a saddle, right? You can picture a saddle, and I could try to draw this, but I'm probably going to embarrass myself. So here's the part of the saddle you sit on, and then in the other dimensions, it kind of curves up, and it kind of pictures the top one curved. So part you sit on, part that goes up to keep you in the saddle, right? That's a saddle point. The point in the middle is a critical point because in 1 dimension, right, you curve up, and the other dimension you curve down. So at that point, you have 0 derivative in each direction. However, because the dimensions work opposite, one is convex and one is concave, the saddle point in the middle is actually not a minimum or a maximum, it's just a saddle point. So it's not an optimum and we don't actually want it. So those are the possible cases. Now we can look at how to actually compute whether or not you have a positive definite or a positive definite or a negative definite Hessian. If the eigenvalues are all positive, you have a positive definite matrix. If all eigenvalues are negative, you have a negative definite matrix. If they're mixed, you have a saddle point. And if the determinant equals 0, then we know at least one eigenvalue is equal to 0. So we have an indeterminate. Missed the N. Okay. So that's it. That gives you a sense of how it works, and that's how you use these things. And that's another reason why we learned how to calculate eigenvalues back at the end of the previous part of the course, because we can use eigenvalues to determine if our Hessians were positive or negative definite, which tells us if we have a local minimum or maximum. So now that all said, well, 1 second, I'll get back to that. Okay, so that's step 4, is to figure out if the Hessian is positive or negative definite, and then depending if it's positive or negative definite, we know if it's a local minimum or local maximum or neither. Okay. Step 5 is to compute the value of the function at all critical for all critical values and compare. The biggest value is the global maximum, and the smallest value is the global minimum. And there's no bounds here, so we don't have to worry about bounds. We just have to compute, if there's more than one critical value, we have to compute F for all of them and compare minimum to maxima. And that's it. That's the end of the step. That's the end of the steps, and that's the entire method for doing this. No, you do have to calculate, you do have to compute the Hessian here, because if you have a saddle point, right, you could compare the point to the saddle point, but that's going to be neither a minimum nor a maximum. So if you have a thing that looks like this in one dimension, right, and then this in the other dimension, it's not going to have any minimum or maximum, right, because it goes on forever, all the dimensions up, so the maximum is infinity, and it goes forever down, so the maximum is negative infinity. The fact that the point in the middle is a saddle point, is a critical point, is irrelevant. So the positive parts about all this, no new intuition, no new complications theoretically. It's exactly the same idea as before. You compute critical points by setting the first derivative is equal to 0. You find the second derivatives for the critical points. You figure out if they're corresponding to local minimum or maxima, and then you compare all these values to see what's the biggest one, and you're done. Same exact conceptual ideas, no new intuition. Downside is that the actual computation of these things is more complicated and can be much more complicated. Oftentimes so complicated you would not do it yourself and you let a computer do it for you. But sometimes you do need to do it for yourself. And so in the next module, we will go through and do a couple of examples of how to do this. There's more examples in the book. There'll be more examples in the problem sets and the problem sessions. And it's good to just practice, because all this stuff is practice. There's really nothing conceptually difficult to this. Once you've mastered the basic understanding of optimization that you got way back in part 2 of the class, there's nothing new. It's just getting used to the method of doing this, and that's just practice. So we'll start practicing in the next module. Thank you very much.